Hello everyone, my name is Prithvi Kake, student of Shri Venkateshwara College of Engineering. I'm currently pursuing my engineering degree under CSE AI stream. My USN is 1VE23CA036, SEM 3. Course title Mathematics 3 for CSE stream. Course code BCS301. And today's topic is about Markov's chain, definition, basic concepts, and explanation of Markov's property with examples. Firstly, let's see its definition. A Markov chain is a mathematical system that experiences transitions from one state to another within a defined state space, with the probability of each transaction depending solely on the current state and not on the sequence of the events that preceded it. The property is called Markov property or memoryless property. Introduction. A Markov chain is a sequence of events in which the probability of each event depends only on the state of Markov's event. Named after a Russian mathematician, Andrei Markov, these models are fundamentally in probability theory and have a wide range of applications in various fields, like mathematics, physics, and economics, computer science, and biology. The key characteristics of Markov chain is its memoryless property, meaning that future state depends solely on present state, not on the sequence of events that preceded it. These chains can either discrete time where transitions occur at set of intervals or continuous time, representing use of transition matrix that lists the probability of moving from one state to another. In practical use, they model systems like weather patterns, stock market trends, and even board games where each move depends on the current position. The state in Markov chain can be finite or infinite, with the state representing possible condition of the system. These models help in predicting long-term behavior by analyzing the steady state conditions. These models help predicting systems in given state after many transitions. Markov chain have also been fundamental in development of algorithms such as Google's PageRank, which ranks the web pages in search engines results. Basic concepts. States. A state represents a specific condition of situation in system. State space. This is a set of all possible states in Markov chain. Transition probability. This is a probability of moving from one state to another in a single step. Transition matrix. A matrix that lists the transition probabilities between each pair of states. Initial state distribution. This describes the probability of the system being in each state at starting point. Markov property, also known as the memory loss property, it states that the future state of the system depends only on the current state, not on the path that led to the side of the state. Absorbing state. A state is called absorbing if once entered it cannot be left. For example, a game that ends when a certain condition is reached would have an absorbing state representing the end of the game. Steady state distribution. This is a probability distribution over the states that remains constant over time in Markov chain. It represents the long-term behavior of a system. Recurrent and transition states. A state it is currently if the system will eventually return to it no matter whether it starts or ends. A state is transist if there is a chance of system may never return to the state. Example, let's use a simple example of weather to explain the basic concepts of Markov chain. For example, we take three conditions. Imagine a weather model where the three states are sunny, cloudy, and rainy. The weather on the given day depends only on the weather of the previous day, which fits the Markov's property. Transition probabilities. The transition probabilities define the likelihood of the weather changing from one state to another. Let's assume the following probabilities. If it's sunny today, there is a chances of 60% chance it will be sunny tomorrow, 30% chance it will be cloudy tomorrow, and 10% chance it will be rainy tomorrow. If it's cloudy today, there is a chances of 40% chance it will be sunny tomorrow, 40% chance it will be a cloudy tomorrow, 20% chance it will be raining tomorrow. If it's rainy today, there is a chance of 20% chance it will be sunny tomorrow, 50% chance it will be cloudy tomorrow, and 30% chance it will be rainy tomorrow. We have converted the probability in table form, and each row in this matrix represents the current state and each column represents the next state. The sum of the probabilities in each row is equals to 1, indicating the weather must transit to one of the states. Initial state distribution. Suppose we start with a sunny day, which means the initial state distribution is sunny 100%, which is 1.0, cloudy 0%, and rainy is 0%. Markov property. The future weather depends only on the current weather, not on the sequence of previous day. For example, if it's sunny today, the probability for tomorrow's weather are determined solely by the sunny row of the transition matrix, regardlessly how many sunny or rainy days there were before day. Steady state distribution. The steady state distribution tells us what the weather will be in the long run, regardlessly of the initial condition. It represents the probability of each state of the Markov chain has run for a long time. For this example, after many transitions, we might find the steady probabilities coverage to something like sunny 50%, cloudy 30%, rainy 20%. This means that over the long time, there will be a 50% chances of sunny day, 30% chances for a cloudy day, and 20% chances for a rainy day. Summary of these concepts in the example. States: sunny, cloudy, and rainy. State space: sunny, cloudy, rainy. Transition probabilities: the likelihood of moving from one weather state to another. Transition matrix represents the probability of transitioning from one state to another. Initial state distribution, the starting weather condition. Markov property: tomorrow's weather depends only on today's weather. Steady state property: the long term probabilities for each weather state. Conclusion. Markov chain are mathematical models that describe system transition from one state to another based on a certain probabilities. These operate under the fundamental principle known as Markov property, which states that the future state of the system depends only on its current state and not on its past states. These models are commonly represented using a transition matrix which countlessly the probability of moving from one state to another in a sequence. Markov chains are widely used in various fields such as finance to predict the stock market trends and in weather forecasting to estimate the likelihood of different weather patterns. They come in two forms: discrete time Markov chains, where the changes happen at fixed intervals, and continuous time Markov chains, where transition can occur at any time. The concept of steady state distribution helps in understanding the long term behavior of the system. Significant role in machine learning algorithms, especially in natural language processing tasks like predictive text and speech recognition. Their versatility extends to board games and sports analytics, where they are used to analyze game strategies and player performance. The simplicity and efficiency of Markov chains make them an essential concept in probability theory and statistics. Despite their simplicity, they provide powerful insights into the dynamics of complex systems in both theoretical and practical applications.